All right, hello everybody, and welcome to the Great Rocket Challenge. You all are going to be aerospace engineers today. An engineer is someone who designs solutions to problems. Your problem today is to design the most cost-effective air-powered paper rocket possible. So, let's learn a little bit about how rockets work. Here is a real rocket, a Delta IV Heavy, which launches satellites into space. Now, a real rocket has these fuel tanks which carry fuel and oxidizer. The fuel and oxidizer mix inside a rocket engine where they ignite, creating an explosion. Explosions typically go outward in all directions. The job of a rocket engine is to take the force of that explosion and direct it all in one direction, going downward. Our rockets today aren't going to use combustion because we're probably going to do this indoors. So instead, we are going to use air pressure. So how does a rocket move itself? Well, a rocket uses Sir Isaac Newton's third law of motion. It states that for every action, there is an equal and opposite reaction. Imagine you're on a skateboard and you want to move forward. To do that, you push your foot backward against the ground. Well, a rocket does a similar thing. A rocket is full of fuel. It combusts that fuel in an engine and shoots it out the back, creating a force called thrust. Now, the action of accelerating that fuel out the back, generating the thrust, creates an equal and opposite reaction, pushing the rocket forward. An advantage of this is a rocket can work out in space where there's no gravity, there's nothing to push against, there's no air. Just the action of generating the thrust propels the rocket forward. So, if a rocket generates 1,000,000 pounds of thrust, then 1,000,000 pounds of force are going to be pushing that rocket forward. So your rocket today is going to use air pressure, so it's not going to have an engine. It's also going to be flying within Earth's atmosphere. So let's see the parts of the rocket that you're going to build today. A rocket has a body, also known as a fuselage. A rocket body is the main tube of a rocket. Now, on a real rocket, which launches spacecraft into space, the body is what contains the fuel and oxidizer tanks. And there's some plumbing inside, which carries the fuel and oxidizer to the engine. Now, your rocket today has to contain air pressure. So when you make your rocket body, try to make it as airtight as possible. Now, our rocket is going to be traveling within the Earth's atmosphere, so it needs to be aerodynamic. In order to make your rocket aerodynamic, it has to have a nose cone. Now, the goal of a rocket is to accelerate as fast as possible. If you launch a satellite into space, you have to accelerate it up to a speed of 17,500 miles per hour. And so as a rocket is traveling through the atmosphere, we want to reduce the amount of speed lost to drag, or air resistance. A nose cone helps a rocket go fast by reducing drag. It's pointy, and it diverts air around the sides of the rocket body, and that reduces aerodynamic drag, or friction. Now, how do we guide our rocket, and how do we keep its nose facing the correct direction as it flies? Now, our rockets are going to include fins, or aerodynamic stabilizers. A fin is very flat and very sharp, but it has a lot of surface area on the sides. And so if your rocket is flying straight through the air, its fins slice through the air like a knife, and they don't induce very much aerodynamic drag. However, if your rocket starts to turn this way or that, away from the direction of travel, its fins are going to start to induce some drag at the back. The nose isn't going to induce much drag because it's so pointy. So the drag at the back is going to snap the tail backwards, facing the nose forwards. And this helps your rocket to fly in a nose-forward attitude. Now, if you build a controllable rocket, you can control the flight path by actuating or changing the angle of the fins on the rocket. Now, real rockets that fly in space today typically don't have fins or stabilizers because they don't spend much time in the Earth's atmosphere. And so they mostly steer by gimbaling, by steering the nozzle of their rocket engine, which angles its thrust to help turn the rocket and keep it in balance as it launches. Now, one other thing about a nose cone. Typically, the nose cone is where the satellite or the astronauts are housed. And typically, if we launch a satellite, you need your nose cone when the rocket's in the Earth's atmosphere, which only lasts about 2 minutes. Once you're outside the Earth's atmosphere, your rocket doesn't need to be aerodynamic anymore, and you want to save weight so you can accelerate as quickly as possible. And so a real rocket has what is called a payload fairing that creates a nose shape at the front of the rocket, but as soon as it gets above the Earth's atmosphere, that separates to save weight. So those are the basic parts of the rocket that you're going to build today. So you all are going to work in teams. Each team has a budget of $1 million. You're going to have a certain amount of time to build, and your instructors are going to give you warnings as they count down how much time you have left. The prize for the winning team is a launch contract for $10 billion, and the winning team will receive a giant check made out to $10 billion. Now, the winning team is whichever team has their rocket travel the furthest for the least amount of money spent. You are going to take the number of dollars you spent and divide that by the distance your rocket traveled to calculate how many dollars you spent for each unit of distance. The team that spent the least amount of money per unit of distance will win the challenge. So if your rocket goes really far, but you spent 10 times more money than any other team, you might still lose. So we are going to follow the engineering design process. We have stated the problem, which is to make the most cost-effective air-powered rocket possible. You're going to generate ideas, figure out how you want to design this rocket. You're going to select a solution, which is going to be the design you come up with. You're going to build a prototype rocket. You're going to evaluate that rocket through a test launch. And then we're going to compare our results to determine whose rocket was most cost effective. Now, on your teams, there are going to be several jobs. If you have fewer people on your team, you can combine these jobs, have one person do multiple jobs. The project director, they're in charge of all final decisions. If your team cannot convince your project director, they can override your decisions. Now, as you build your rocket, you will have to pay for your items by writing checks. The project director is the person who's going to sign off on the checks. The budget director is going to track your spending and purchase your materials. When we open the store with all your supplies, they're the only person who can go up to the store to purchase your supplies. The chief design engineer is going to plan, design, and build your rocket in compliance with decisions made by your team members. They're the chief engineer. The safety and compliance supervisor is going to be in charge of inventory and enforce regulations. Once your rocket is complete, they will perform the launch. As soon as the build time is over, no one may touch your rocket other than the safety and compliance supervisor. If you have any extra people on your team, we can have ambassadors who can consult with other teams. We do not allow spying. That is corporate espionage, so you will be fined if you're getting ideas from another team without their consent. An emission specialist may assist any other team members as necessary. So in a moment, you can form your groups and decide who on your team will take which roles. Now finally, here is your subcontractor list. These are the things you're going to have to purchase. Every team must purchase a rental of the launch pad. A rental of the launch pad will cost you $150,000. If you don't write a check for the rental of the launch pad, you will not get to launch today. Now, our rocket fuel is air pressure in units of pounds per square inch. We're going to charge $1,000 per PSI. We recommend that you purchase somewhere between 10 and 30 PSI. Any less than 10 and your rocket might not get off the launch pad. Any more than 30 and your rocket may explode on the launch pad. If your rocket explodes, we will measure the distance to the furthest piece of debris. Now, paper products. Your rockets will mostly be made out of paper. A regular sheet of copy paper will cost you $75,000. You may notice there's a bit of a markup on these items. These are aviation grade materials and they have been tested for quality control. Sheet of construction paper costs $150,000. It's a bit more rigid and heavier than copy paper, and most importantly, it comes in different colors, and you can pick the color of your copy paper. Cardstock costs $225,000. Like copy paper, it's white, but it is even heavier and more rigid than construction paper. Specialty paper is $350,000 per sheet. Now, specialty paper, you have the choice between a sheet of cardboard or a sheet of tissue paper. Adhesives to hold your rocket together. Unlimited use of one glue stick for the time of our build is $50,000. 50 centimeters of duct tape, which is about this much, is $100,000. The same goes for clear tape. Masking tape is also $100 for twice as much, a full meter of masking tape. Now we have some other optional items as well. So metal weights can help to adjust the center of gravity of your rocket. One metal weight is a paper clip, and we will charge you $4,000 per paper clip. String, if you can figure out anything useful to do with that, will cost you $10,000 per meter. Now, your instructors might have some advice they can give you. Their wisdom, however, will come at a cost. Every technical question about decisions you're making on how to best build your rocket will cost $3,000 per question answered. Now that $3,000 might be wasted. That $3,000 might be very well spent. And finally, if you can't figure out how to make the nose or how to make the fins, we do have templates for you. The templates are like stencils, and we charge you by the minute of use. So 1 minute with the nose cone template will cost $10,000. 1 minute with the stabilizer template will cost $15,000. Now when you use them, make sure to return them to the store within 1 minute. If you don't return them within 1 minute, you will be charged for a second minute. So with that, you may now form your teams, decide what jobs you want to take, and you can start building your rocket. The store will open in just a few minutes. Good luck, rocket scientists.